हेलो 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 हाँ हाँ आसुची हेलो हाँ हेलो हेलो
Okay, everybody, let's get started. So now the formal inauguration is over, so now the fun begins, right? So all right, so we did have a little round of introduction. What I usually do is I usually start the my courses by doing a little introduction. Everybody got the homework 0 yesterday. Is anybody here who is not part of the WhatsApp group? Everybody is good on WhatsApp? You're already added and stuff? Okay. So I have received, I think, already 10 or 11 submissions. Those of you who have not, please do that. There is a reason I collect that, and you will know that at the end of the session. And also, there is a question about your favorite song. Remember? There is a reason I also do that. So I am a very, very big music fan. I listen to music all the time when I'm working, and it's very difficult to look for new songs or select songs. Every time I teach, I collect my students' best songs, make a playlist, and that plays for me. So I have like 10 or 11 playlists every semester I collect from my students. It can be any language. I literally listen to all songs. So if you want to talk music sometime, I'll be happy to do that. So it's not fair for me to ask for your introduction and not introduce myself, right? So that's the first thing I do always is Capital High School, Bhubaneswar. Anybody from Bhubaneswar, you should know that. The people don't go to Odia medium anymore, so you all may not know what this is. It used to be an Odia medium school. I think Umesh is also an Odia medium. Where is he? Disappeared right there. Okay. So then BJB College, then IIT Kanpur, Texas Tech, couple of years, University of Illinois. I stayed there for 8 years, and then I have been teaching mostly pavements, railroads, transportation, geotechnics. At Oklahoma State, I actually teach the Intro to Geotech class every semester, which is one of my favorite classes to teach, because as I said, those of you who are working in the field of transportation infrastructure or pavement or anything, trust me, no pavement engineer is going to have a solid foundation unless you know geotechnical engineering. It's an absolute must. So every famous geotechnical pavement engineer you can imagine is actually a geotech by background. You start from the Carl Monismiths, the Richard Barksdales, the Marshall Thompsons. Their foundation is all, and in the modern greats like the Iyad Masad, the Imad Al-Qadi and stuff like that, all of them are very, very strong foundation engineers. Okay. Then Umesh, do you want to say a little bit about yourself? This is your slide. No? Okay, I'll continue. Umesh has been a good friend. By the way, one more thing. There are some PhDs. I think Ottanu, where is it? Ottanu, somewhere sitting right there. He's a PhD, and some other people are PhDs. So I've been in the US for 20 years, right? So I am very much into first names. I will not call you Dr. Behera. I'm sorry, it is not out of disrespect. I will call you Ottanu. You can call me Deb too. That's fine. I'm a very informal person. So anyway, Umesh, he's been a good friend for several years now. He has been the primary person that has connected me to IIT Bhubaneswar. Tanmay is somewhere here, right there. Tanmay is actually a student that we are co-advising. It's been a lot of fun working with them. So he's the host faculty and stuff. So you do remember one thing about this class is, this is probably the only class you will attend where the instructor actually encourages you to use your cell phone. So get out your cell phones. Everybody has a smartphone, right? Does anybody still have a flip phone, old Nokia? No? Good. Smartphones. We need a smartphone. Let's do this QR code quickly. Okay? So this is a thing called Mentimeter, where we are going to monitor several things. Sometimes this thing creates issues. Okay. PhD scholars. How many are submitted? Others. This is the class composition, what we have right now. So go 10 masters. Where are the faculties? You don't have your cell phones? I know there are at least couple. Or maybe faculties are slow in using cell phones. Reasonable explanation, right? No? 23? Some people have not submitted it yet. How many do we have? I have to. I think there are more than 23 people in this room, aren't there? Some have not. Is it not working for some people? Okay, so that's the composition. Okay, a lot of master students. So that's good. That's actually in a way good. I do have some fundamental stuff in here that we are going to cover, which at a master's level you'll find more useful. If you're a PhD or a postdoc, you may already remember this, may not remember this. We'll go through that quickly. Okay, and I said this already. You are going to submit this. It's mandatory. If I don't see somebody, I'll chase you down. So please submit this whenever you get a chance. Number 5, I was actually a little bit disappointed by some people saying that I don't have any unique experience. So I'm going to give an example, and then I will give you all the chance to modify your answers, those of you who have submitted. Okay. So I have a unique experience that I can guarantee you will not hear from anybody else in your entire life. That holds for every country. This holds for America, holds for India and everywhere. And I am the only person that you will ever know that was once bitten by a dolphin. So here goes the story. So I went to Florida. This is back, I think, to 2012 or something, with myself, my wife, my mother-in-law, and my brother-in-law. We went to Florida, and there is a program called Swim with the Dolphins. Okay, so what you do is you go in the middle of the ocean. This is like south, right? It's basically where the Atlantic and the Gulf of Mexico join and stuff. So you can actually swim, and there are a lot of dolphins, and people swim. And I love swimming in the open water. So the captain was keeping telling me that, why don't you swim, why don't you swim, why don't you swim? I said, no, these are wild animals, I should respect them, I should not swim with them and stuff. So he's like, no man, you paid all this money, you should go and swim and stuff. And I'm like, okay, we should probably do that. So then I went to the water, right? So what happened is, for about half an hour, there was a mother dolphin and a baby dolphin that were following the boats, and they were looking for food and stuff. And remember, I don't know what you know about dolphins. They are big, okay, and especially when in water, they're really big. Like I'm talking, the mother dolphin was about 9 feet long, and the baby was probably about 5.5, like probably my height, 5'8", 5'6", 5'7", something like that. So then I was swimming, and then all of a sudden, what happened? The baby dolphin just came to me. So that's my brother-in-law taking pictures. He didn't know it would become like a story. So that's the baby. Okay, you can see how much long it is. And then it just went down, and I was trying to swim, right? So it went down and it grabbed my arm like this. And then I was in deep water. I said, I told the captain, I was near the boat. I told the captain, I said, hey, it's trying to bite me. I said, yeah, you'll be fine. I said, what the heck do you mean you'll be fine? I'm going to die in the middle of the ocean or something. So I pulled my hand, and it basically, this is the teeth and stuff. So it basically did a complete, like almost like a little saw bite or something like that. And then I tried, and then it went away, and it was trying to come back to me, and I literally punched it. I literally almost boxed it, and then it went out and stuff. So that's my unique experience. This is a picture I show everybody in every semester I teach classes and stuff, and I ask for it. So now you can go back and revise your submissions if you want. I'm sure people you have unique experiences. So yeah, that's why I say this. This helps people to remember each other. Okay, how are you going to do this class? We're going to start about 9:45 every day. We'll go till about 11:15. Then from 11:15 to 11:30, we'll have a short tea break. Then 11:30 to 1. And then 1 to 2, I think, is lunch. Is that correct? 1 to 2 is lunch. Okay. And then we'll do a hands-on exercise from 2 to 3:30 or something. And the whole idea here is, and the good news is there is so much student, so I don't feel bad pushing you guys to do things. What you should do is bring your laptops, and I will give you today I'll give you a paper, you're going to read it, and it's something called statistics driven borehole location or soil sampling. Like for example, if you are given a 60-kilometer road to construct, and your boss or your budget says you have only 100 boreholes or soil explorations you can do, how do you do that? Where do you place them? Where are the 100? Is it always divided by the distance, or is it based on some prioritization? That's what we're going to do. So basically what you'll do is, today is the first class, so I didn't want to give it in advance. So today during the tutorial you're going to read the paper, most likely you will not finish it, we'll see, and then I want everybody to build a spreadsheet for a problem that I'm going to give you so that you know how to do this and stuff like that. Then as we move along, we'll do other things like, I have triaxial testing data. I'll give it to you, and then it's up to you. You can write a Visual Basics code, a Python code, a MATLAB code, or whatever you want to do to read the data and spit out whatever you want to do and stuff. So that's what the tutorial is going to be. So bring out your laptops and stuff, and we'll do that. So today we're going to talk about the design philosophy and historical development. Okay, so show of hands, how many of you have taken a pavement design class in your life? Okay, most of you. That's good. Okay, so we're going to talk about the historical development, how things started, what is the philosophy, how the philosophy has changed over time, and what's happening with respect to the modern designs and stuff. And then we're going to go into railroad and pavement substructure layers and their importance. And there are some of you have actually asked some interesting questions in your submissions, which was actually pretty nice, saying that, okay, what can we do this? What are the concepts? Why is our design state in certain condition in India versus other countries and stuff? So we'll address some of that and whatnot. And then we will try to end up with something called mechanistic empirical pavement design framework. Now, the good news is, and we'll get to that at the end of the day today, but the good news is if you look at a railroad structure and if you look at a pavement, it's actually not very different from each other. In a pavement, the tires are going directly on top of an asphalt or a concrete layer, whereas on a railroad, the train is going on a rail, the rail is going to what is known as cross ties or sleepers, and underneath that it's the same. Underneath that it's the same. As long as you just combine what is known as a beam theory, continuously supported beam or something, with a layered elastic formulation or something, that's what your railroad design is. So the good news is all the concepts we're going to talk hold for both the systems. So that's how, pretty much any railroad engineers you see, they also have a very good background in pavements and stuff, because the systems are very similar. It's all based on mechanics and stuff. And the tutorial today, we're going to do the statistically based soil exploration and compaction control approaches. So day 2, tomorrow we're going to do subgrade evaluation. Like you are going to have, you are an engineer, you need to go and construct a pavement, and then let's just say it's a realignment or a new alignment and whatnot, or I think there is some bullet trains coming and stuff like that, so you're going to do that. So what is subgrade evaluation? What are the methods? What do you recognize? What do you look for? What are the important properties and stuff like that? You probably know that pavements are the only infrastructure that are designed to fail, right? You don't design bridges to fail. That's going to be disaster. You don't design this building to fail and stuff. Pavements, you can design them to fail and stuff. So what is failure? What is the meaning of failure? What is the meaning of, what kind of properties do we look for? People who have a very strong geotech background, you probably know what is bearing capacity failure and stuff like that. I mean, is bearing capacity something that's important for pavements? Is that relevant? What are the properties that are relevant, right? What kind of stresses and strains do we talk about and stuff like that? So this is a good time for me to ask, and please don't hesitate. That's why we are here for 5 days, and I don't mind going over anything. How many of you are confident that you can tell me the difference between stiffness and modulus? Raise of hands. I saw a couple nodding their heads in a negative, and that's good. I appreciate that. That's what I want. How many of you can tell me the mechanics difference between stiffness and modulus? Okay, we'll get to that, because that's very important. That's very important for you to understand what's going on in pavements, in a layer, in whatever you are trying to determine. So how many of you have heard of the test called CBR, California Bearing Ratio? Most of you, right? Except for BTech students, I'm pretty sure. Yes. Okay. So what is it? Why do we use CBR? What is it giving us? How representative is it of what we are trying to measure? Is that a good measure? Is that a bad measure? If you are in the middle of nowhere in Africa and then you need to do some quick tests, is CBR a good thing for you? But what if you are a researcher and you're trying to advance the study and stuff? Do you still rely on CBR and stuff like that, right? Those are things that we're going to discuss tomorrow. Okay, laboratory and field methods, that's what this is. CBR, DCP, I think a lot of you have heard of it, dynamic cone penetrometer. We'll take a look at that. What does that give us? Why is that a useful tool for us and stuff? And then we're going to talk about laboratory and field methods, others, continued falling weight deflectometer. I'm sure a lot of you have heard of it. Some of you may not have. We'll take a look at that. There is something called lightweight deflectometer. So what is that? What is the concept? How does that work? What do we get out of it? There's something called geo gauge or a soil stiffness gauge. We'll take a look at that. And then tomorrow's tutorial will be CBR, DCP, and FWD data, where I will actually give you some data from real field experiments that I have run, and then I'm just going to have you interpret that and come up with some target numbers and stuff, saying that, okay, what do you understand about this soil? What is the average CBR? Because guess what? If you are making concrete, you know, okay, this is 4,000 psi concrete. If you are a geotechnical engineer, you have absolutely no idea what you're talking about, right? You're standing at one place, you do the measurements, 10 feet away, it can be completely different. So that's the reason. How many of you have heard, this is more of a question for the seniors, like PhD students and stuff. How many of you have heard the name M.R. Madhav in geotechnical engineering? Just one? Okay. Are you from Hyderabad? You know him? Okay. So M.R. Madhav was probably one of the most famous geotechnical engineers that India has produced. At least I would claim that's because I'm a big M.R. Madhav fan. He was a professor at IIT Kanpur. Then I think he's still teaching in some Hyderabad universities. Sometimes he does. He's one of the legends of the field, and he used to say this thing. This is when I was an undergrad, my very first geotech class, and his first class, he says, geotechnical engineering is a science, but its practice is an art. That basically really influenced me, and that's how I applied for a master's and stuff. So it's very, very intuitive. It's very, you have to be an engineer to understand what's going on. You can't be a true scientist to do geotechnical engineering. You have to have some notion of, okay, this is approximation, this is good enough, this is what it's going to work. Day 3, we're going to go into shear strength, modulus, permanent deformation. I saw one question, I don't remember the name, but I found it very genuine. That person said that I am a little weak in geotechnical engineering concepts. Is that going to affect my understanding of the course? The answer is no, but the point is, if you still leave this class being very weak, then I have not done my job. And I like to do my job. So we're going to go over some of the things, like how many of you have ever seen, okay, let's go the other way. How many of you have run a triaxial test ever? Either repeated or static, it doesn't matter. That's a pretty fair number. How many of you have seen a triaxial test run? Most of you? Okay. So we're going to go really deep into triaxial testing. Why triaxial testing? What is triaxial? Okay, let's this is still in introduction. Who can tell me why is a triaxial testing cylindrical? Why is the sample cylindrical? Let me explain. What is triaxial? 3 axes, right? What is the 3 axes that we see? What's your name? Dhruv? Dhruv, what are the 3 axes in real world? Sit down, never get up, please. What are the 3 axes in Cartesian coordinate? X, Y, and Z. So this, 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 right? So it should be cubical, isn't it? Isn't it cubical? Why is triaxial testing cylindrical? Hold on, say it again. Yeah, radial. You are assuming all the radials are same, but why? Is it always? Can you guarantee that? No. That's cheating, right? It's like I'm not going to clean my house because I'm lazy, right? You need to fix your boundary condition. That's cheating. I mean, you're right though. I mean, you are absolutely right that boundary conditions are easier to avoid in a cylindrical. But why? Why are we doing cylindrical? Same as boundary condition, same answer, but that's not the reason. Why do you do it? Again, it's assumption. I'm talking about triaxial. You call it triaxial. How many of you seen a drilling in function in operation? Have you seen a drill in operation? How does a drill move? In a circle. How are you coring the soil? In a circle. So what kind of sample are you going to get? That's the reason cylindrical triaxial tests, because you're trying to replicate what's in the field, right? So we're going to go into all of these things. You never ever go and do a in the soil. You never do that. You do a drill. That's circular. That's cylindrical triaxial testing. That's the reason we do that. We'll get into a lot of that. We'll get into some more circles, some failure envelopes, some drained and undrained, and then we're going to go into some shear strength data. Day 4, probably by far my best topic of my entire life, because I spent my entire PhD doing this, which is known as repeated load behavior. Okay, what is repeated versus what is cyclic? What is cyclic? Regular intervals loading will occur, mostly correct. You're missing one little. Okay, let's go to math. You're all, we're in India, so we don't have an excuse to escape mathematics, right? We're supposed to be strong in mathematics. In America, I don't have that excuse. I cannot blame them a lot of times, because the students, they come, the high school system is very different there. But here I know, I studied here, right? So give me a example of a cyclic function. Sinusoidal, good. So how does a sinusoidal go? Sine 0 is, sine 90 is, sine 180 is, 270 is, minus 1. What does that mean? It has a positive component and it has a, so if I am applying a loading, what am I doing to the sample? Positive and? Go ahead, you said it right. Positive and negative. How many times do you run a resilient modulus test and you push the sample and then pull it back? You never do. So anybody who tells them that a resilient modulus is a cyclic test, they have no idea what they're talking about. It's not a cyclic test. It's a repeated test. Because it is positive, gap, positive, gap, positive. There is a history, right? Is that the same as mod of sine? Haber sign. What is Haber sign? No, it's not. Who remembers what is Haber sign? Come on, mathematics. What is Ver sign? 1 minus cosine theta. What is Haber sign? Half of Ver sign. 1 minus cosine theta divided by 2. So what is that? Sine square theta over 2. The 2 is gone. So sine square theta over 2, not theta anymore, it's a theta over 2. Why is that important? Somebody like Tanmay, he's actually building his own triaxial testing system. He needs to know all of this so that he's going to program the signal going into the system, right? It's not a sinusoidal wave. It has a rest period. Why is the rest period important? We're going to talk about all of that. So day 4 is going to be a lot of this. Day 5 is stress dependency. A lot of people will say, what is the resilient modulus of this soil layer? Right? The fun answer to that is you can get by as saying it depends. And you're still right, because resilient modulus is not a constant number. It depends on stress state. But we are still doing an E value in our designs, right? So what's the E? What does it represent? What stress state are you talking about? Is that a representative state? Is it at the top of the layer? Is it the bottom of the layer? Is it the middle of the layer? How does the stress bulb dissipate? Do we ever think about these kind of things? What's the difference between Young's modulus and resilient modulus? Everybody has seen Young's modulus, right? Vishwabandita, you have seen Young's modulus already, correct? What year are you in? 3rd year. So you've probably done mechanics already. So what is Young's modulus? Stress over strain? Boom, right? Linear, right? What's resilient modulus? Is that the same? Is the resilient modulus an elastic modulus? We'll get to that. The answer is yes, but we'll get to that. Okay? Then we're going to do a little. Does everybody have a Windows based computer here? Except for me, I have a Mac, but that's okay. Does everybody have a Windows based computer? Yes, okay. So I'll give you this software called IIPave. It's free, so I'm allowed to distribute this. So this is finite element based pavement analysis program, and we're going to do some analysis to see how the stresses and strains are changing and stuff. At the very end, we're going to talk about anisotropic behavior. You said about the lateral stresses are the same. Is it actually the same? How does an aggregate layer or how does a soil layer behave when you compact it? Is it actually isotropic? Is it anisotropic? Is it truly anisotropic? If it is truly anisotropic, it should be this, this, and this, 3 different values. Is that how it works? Right? Are there any reasonable assumptions that we should be able to make and stuff like that? Any questions? And that should be day 5 for us, and then that should give you a good enough foundation to and I'll introduce, of course, resilient modulus models. You have heard of something called K theta model, universal model, MEPDG model. We're going to talk about what is MEPDG, why the heck it is the way it is, and stuff like that. All of that stuff. Okay? Any questions before we go about the course structure or anything that I missed that you would like to see? It's a live curriculum. I can change anytime. It's not fixed. All right. So that's introduction. Now let's jump in. Okay, this course will assume in-depth understanding of basic geotechnical concepts and mechanics, but again, we're going to cover whatever I see is not. And please listen, you have spent the time to come and spend five days here, so please don't be shy. If you don't know anything, raise your hands, right? The smart person asks questions, right? The people who underestimate others, who ask questions, are the real dumb ones, right? We're going to do basic understanding of pavement engineering. What are critical pavement responses? Why is that important? What is the difference between response and performance? What is mechanistic empirical? What is empirical? What is mechanistic? Why are they different? What are the advantages of each versus the other and stuff like that? If you're not familiar with some of them, talk to me, spend sufficient time. I will give you enough materials. Get out your cell phones. It's the same code, by the way, I think if I'm not wrong. Wait, you can actually stay there and I should be able to start this. Start Menti. What happened? Why is it doing that? That's not fair. Oh, I see. Yeah, there it is. Okay. What do you see on your slides, on your Mentee thing? Is it the first question still? Okay, yeah, that's what it's saying, right? Hold on. I don't know why it is doing this. Let me see one thing. Slab display. Okay, now it should do that. Do you see a screen now? Okay. How well do you remember the following geotechnical engineering concepts? 10 is very confident. You need it again? I thought it should refresh. Okay, let's try that. Or do I, is it catching? Okay. These are average scores, by the way. Last time I think I had 23, 22, 23, 24, 26, 7, 8. Okay, this is interesting. I didn't expect this to be higher than that. That's okay. We'll see that. Compaction is not something that we will go very deep into this one. But we will touch it and see what's going on, and then we will spend a lot of time on shear strength and repeated load. So you should be able to catch up on whatever is lacking and stuff. Okay. Okay, let's do this. Historical. So first of all, the slides use this in course. It's been compiled from a lot of courses I have taken, presentations I have made, colleagues I have worked with, professors I have had. So it's a lot of their credit. I have just reorganized some information. Some slides I just use directly. So I'm just the messenger. I always like to say this because credit needs to be given to people who deserve it. Okay. So what are the learning objectives after this end of Umesh? We don't need to break for tea again, right? So we can go all the way till lunch. We can go all the way till lunch. Okay, that's almost 2 hours. Okay, we'll see how that goes. Historical evaluation of pavement design methods. Important role that Ashto road test played in the history of pavement design. Recognize the difference between design methods versus analysis and performance prediction methods, right? What is a design method? Design method is where you provide your inputs, and then it will give you a design. It will give you your steel girder should be this size. Your concrete slab should be this thick or something. Is that what you do in pavements? There are some methods that kind of do that, but some methods you do something else. And what that is called analysis and performance prediction, right? So what is the meaning of that? What is the difference between response and performance and stuff? So we will go into all of that. Okay. So everybody said that you have taken some form of pavement design or something, right? So 1950s, it was mostly based on experience, okay? And pavement design was actually done by geotechnical engineers, okay? And you will be surprised that in most state departments of transportation in the US, even today, pavement design falls under the geotechnical division. Okay, pavement design, I am not talking about materials. Materials is different, right? When you are talking about the mixed designs, the viscoelastic, it's not in practice, viscoelasticity is not in practice, but mostly mixed designs, the balanced mixed design, some of you who are working in asphalt probably know that. Performance engineered mixes, which is what in concrete and stuff. So that's different, that's materials, right? But pavement design, when you are designing a pavement structure to withstand loading and stuff, it always falls under, mostly falls under the geotechnical division. And the reason is that they go very hand in hand. The soil exploration, soil properties, unbound aggregates, unbound materials, compaction quality control, all of that goes very, very much into hand in hand. Then question is, 1960s, they started doing what is known as development of empirical methods, right? What is empirical? Anybody? Based on experience, right? When it comes to engineering design, sometimes, I mean, based on experience is still correct, but sometimes it is based on past data, right, which is also experience. I mean, it falls under experience, but it's based on past data, based on observed behavior, based on what has worked, right, versus then. So people started doing empirical methods. They're like, okay, if you have a soil that is, you know, a low plasticity clay or something, just throw in 12 inches of aggregate on top of it, pave with a, you know, 2 inches of asphalt, you're going to be good for a local road or something, right? That's just very, very standard experience based design and stuff. Then people realized that, okay, we're doing empirical testing or empirical designs, and those empirical assumptions are based on our observation, but how many places can we go and observe, right? So, and what are these factors, what are the important factors that are governing my material behavior or structure behavior, right? So let's just talk about things like what factors affect pavement behavior. Akshay, right? Is it Akshay? What are the factors? What you are a pavement designer. I'm telling you design a pavement. What are the inputs you are going to ask me for? Inputs. Say again. Material property. Okay. Yes. That's elastic modulus. That's material property. Okay. What else? No, thickness is you are going to give me the thickness. What other factors? What are the inputs? What are your what information do you need? Traffic. I heard climate. So material, traffic, climate. Mostly all three of them, right? So now we are talking empirical, right? So let's talk about empirical. How many places can you go and observe? What works in Odisha, Bhubaneswar, Odisha, is that going to work in Jammu and Kashmir? Is that going to work in I think even in Telangana and Andhra Pradesh and stuff? No, because the soils are different, right? So empirical is, there is a very, very big, I should not say myth, there is a very, very big popular belief that empirical is always bad, okay? I don't believe in that, because empirical, as long as we are dealing with the data for which the empirical method was developed, it can actually work very well for you. If you really know your motorcycle, let's just say you know your motorcycle like inside out, right? you know that, okay, if I see that this is what's happening, I know I have this many mileage left, I can go, because you know your motorcycle. You don't need mathematics to calculate that. You don't need a mechanic to tell you that. You know your stuff, right? So as long as you are not extrapolating beyond what you observed, as long as you are staying the same material, same traffic, same climate, empirical may just be fine, right? The problem arose when people started taking one empirical method that was developed in Ottawa, Illinois. We'll talk about that, and it was applied all over the world. That's the problem. The problem is not that the method. Yes, it is not 100% based in science, but guess what? Not always you may need that, right? So ultimately, you have to do something that works, right? So then in the 1980s, you have initial mechanistic empirical methods. Okay, what is mechanistic? Follows the principle of mechanics, right? Follows mechanical equations. Good, that's good. What's the what is why can't we just have a purely mechanistic method? Why? You're right, but why? Okay, let's step back. Let's step back. I'm mixing slides here. This is kind of after like just before lunch stuff, but that's okay. We're going all the way till lunch. I'm not. I can mix. What is response versus what is performance? Anybody? Let's go one step at a time. I have a wooden table here. I just came and put a very big load, maybe repeated or maybe got into an UTM, and I've started applying load on here. What is response? Stress, okay, somebody said stress. I think if somebody said, did somebody say strength? Strain, yeah, not strength, strain, good. So stress, strain, we're missing one thing, deformation or deflection, right? That's called response, right? What's your name? Do you drive? Do you ride a bicycle, motorcycle or something? Okay, Himalaya. Okay, so Himalaya is now going on a road tomorrow from here to Bhubaneswar. And he is driving on a road and he doesn't feel happy about it, so he calls Tanmay saying that, hey, you are working here, what is the wrong with this road? And Tanmay is like, this road has a micro strain of 226 or something. As a driver, does he care? Does a driver care about what is the stress or a strain or something? What does the driver care about? What do you care about, Himalaya, when you're driving on a road? Smoothness, very good. What else? Say more. Safety. I don't. Safety can mean two things. Explain a little bit more. Comfort is smoothness. Do you really care about rigidity? Unless you're talking about deflection. That's again smoothness. You said safety, right? Ah, no more. What's that? That's again smoothness. Close. You're all getting close. There is one thing that misses in all of our predictions, which is what? What do you do when it rains, Himalaya? When you are riding? You try to slow down or something, right? But why? Because you lose what? Surface friction, right? So ride quality and surface friction are the two functional things that you really care about, right? As riders, you don't care about stress, strain, deflection. That's the nerd's job, right? You all are nerds here, that's okay, but that's your job. But when you put on your driver hat, you don't care about those, right? So that, my friends, is performance, right? What else do you care about? You said something about ride quality. What affects ride quality? What's your name? Chanchal. Tell me what affects ride quality? No, that's that's what you are governing. What is the road giving you? What aspects of the road affect your ride quality? Roughness, okay, one. Wear and okay, I mean yes, but you're not using terms, but that's okay. What do you see on a road? There you go, potholes. One, what more? What others? Now let's think around lines of potholes. What are the other things? Cracks, transverse cracks, longitudinal cracks. That's what distress is, correct? Right? So now we are talking transverse cracks, longitudinal cracks, rutting, potholes. These are called performance. Right? Another aspect which gets ignored sometimes is the surface friction as well, because we don't have really good models to predict that. That's mostly the reason that happens, right? So we have response, we have performance. A mechanistic approach gives you what, Atanu? The response, right? We are any day, all these master students, these PhD students can take a pen and a paper. They can give me really complicated equations to say that your horizontal strain is this much, your vertical stress is this much, your principal, your what's this called? Von Mises stresses are, the finite element people and stuff like that. But then what? Right? How does that translate to what you just built between Bhubaneswar and Cuttack? Right? You have cracks, you have rutting, you have cracks in two different directions and stuff like that. Performance. You need to link the two somehow. Right? Somehow all the students running your lab tests and doing these beam testing and measuring the flexural strain and stuff like that, they have to be able to say this flexural strain is related to this much alligator cracking when my loading is this much and stuff like that, right? That's the link. Anybody knows what's the link is called? Anybody? PhDs mostly? What's the link between response and performance? They have a name. Transfer functions. Prediction models, yes, correct. Transfer functions. I'm going to give you a reading assignment today by one of my professors, Professor Marshall Thompson. I wanted to introduce this first before giving this. He clearly says transfer functions are the weak links in a mechanistic empirical pavement design framework. Because guess what? We are really good at mathematics. We can calculate stresses and strains any day. We can do finite element modeling. We can do all sorts of advanced viscoelasticity, blah, 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 all of that. The problem is how do you link that into that, right? So that's what mechanistic empirical pavement design is. The 2000s completely focused on implementation of MEPDG, okay? All the way till now. There are still a lot of states, including the state where I am, which is Oklahoma, where implementation has not been very successful, and there is a reason for that, and we'll talk about those, because the transfer functions is what really gets you down. How many of you have heard of the Asho road test? Yes? Okay. So the Asho road test was actually something that happened in 1958 to 1960 in Illinois. But before we go there, here's a little history. You will have this reading there. So early bituminous pavements, there is tar macadams, sheet asphalt, butyllithic asphalt concrete. There is empirical design methods. Then they have some road tests. Then happened the most important event, testing event in the history of pavement design, which is called Asho road test. Okay, By the way, those of you, again, undergrads and junior master students, if you don't know, ASHO doesn't exist today. It's called ASHTO. Okay? It used to be called American Association of State Highway Officials. Now it is called State Highway and Transportation Officials. So there is something called, so it's the road test is not called ASHTO road test, it's ASHO road test, because ASHTO did not exist back then. But now it is ASHTO. Okay? So what they did is they went to Ottawa, Illinois, which is north of Chicago and stuff like that, northwest of Chicago, and they built this test section, and it was a 2-year-long effort, and they had funding from many agencies, some automobile manufacturers, some petroleum industry folks. They're like, okay, we really need to understand what's going on with road behavior and stuff. And then they constructed 6 loops, several test sections, and then several bridges as well. But the fun part of that experiment was the bridges were like this tall. They were not like regular bridges that you have to build an embankment to go into or something. There is a fill and stop. It is all at the same elevation, and the bridges were like little this tall and stuff. So they had some bridge design stuff happening as well. And they had real trucks. The military, the army provided trucks for them, and then they ran it for 2 years. And they collected a heck load of data related to how the pavements were behaving for different sections, different material properties, different thicknesses, different level of loading, blah, 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 all of that. And based on that, there was a lot of analysis, there is a definition of serviceability that they came up with and whatnot, and then they defined how the sections behaved. That became the foundation for pretty much all the pavement design methods moving forward, pretty much until the early 2000s, mid 2000s. In fact, still several states, even in the US, use a version of the ASHTO test, which is ASHTO 1993 or something. You probably have heard of this thing called structural numbers and stuff like that, which that's all coming from ASHTO road test, right? And then you have ASHTO design 72, 76, then 93. After 93, that is probably kind of when people started talking about, more mechanistic things and stuff. And then because they realized that the problem is the ASHTO road test had all the soils were in Illinois, so it was like a low plastic silt kind of a soil and whatnot. It's not very relevant to everywhere in the country or in the world. The trucks that they used, they were running for 2 years, and still the maximum, is everybody familiar with the concept of ESL, equivalent single axle loads and stuff? You probably have heard that. If not, please let me know. ESLs, they have about, I think, close to 10 million ESLs, and that's it. And guess what? If you go to a very busy highway, you can hit 10 million in 5 years easily, right? So the question is, how can we still keep relying on the ASHTO road test data? So this is all on the concrete side of things. So by the way, over the next 5 days, folks, you will realize that most of my examples come from flexible pavements, because that's what I work on. But the good news is transportation geotechnics applies to both. But the saving grace for concrete pavement design, folks, is that the slab carries so much of the load that you kind of have a little bit of tolerance. You kind of can get away with some poor engineering of the soils and stuff, not for flexible pavements, right? So this is 1894 was the first concrete pavement in Ohio, and then they started doing a lot of ASHTO guidelines. They had the Bates test roads. This is a history of the concrete pavements in the US and stuff. And just for information purposes. Now let's talk about, oh my god, really, dude, I made that. This is what happens. Where is mine? It auto corrected somehow. So the test site was at Ottawa, Illinois. 1956 where construction happened. 6 loops and a tangent, half concrete, half asphalt, 836 test sections, 16 short span bridges, and it was inaugurated in 1958 and it ran until 1960, and a lot of testing data was collected and stuff like that. The objective of that, and this is what happens, it's a very good example of something being done and then people not following up on that the way they were supposed to be, and then getting wrong results. The objective of the ASHO road test was that every state DOT was supposed to take that and model some kind of an empirical method in their own state, collect some data in their own state, and then implement it. The point is, when you are working for the government or when you are in the public departments and stuff, you are always constrained by money. You don't have money, right? So people didn't have the money to build their own test strips and stuff like that. So it basically ended up direct usage of the results from Illinois. And of course there is a problem, right? Of course it's not going to work very well. Pretty much Minnesota was, I think, the only state that actually did build a section and stuff like that. So we're going to talk about why am I going over all of this, is we're going to see where transportation geotechniques come into the picture in the big frame of different pavement design approaches and stuff like that, right? So empirical design, simple to apply, but what to do with the new materials, construction procedures, traffic characteristics and stuff like that. So let's, something wrong? Oh, you have a pointer there, okay. I can hear, there is a kind of, oh, thank you so much. This is, it is on, I think. I don't know if it works with Mac or not, that's my only problem. Oh, yeah, allow. Good, that should work, yes. Okay, several of you said compaction was something that you are comfortable with and stuff like that. So let's visit compaction a little bit for a second. What is the method called when the method used to determine moisture density characteristics in the lab? What is the method called? Proctor testing, right? So you know who Proctor was a person, you know that, right? So Proctor was an engineer in California and stuff like that. So he developed this. So you have heard of something called standard Proctor and something called modified Proctor. Why was modified Proctor developed? Heavy loading of compactors, equipment, right? Not vehicles. We're talking about compactors, right? Because the compactors are able to compact a lot better, a lot more efficiently, so they needed to do this after World War II and stuff like that. That's why modified Proctor. Does anybody remember off the top of their head the energy difference between standard and modified? 4.5, good. So yeah, close to 4.5. So new construction procedures, new traffic characteristics, new materials. Somebody said, I think here IIT Bhubaneswar or SBNIT, you're working with recycled aggregates or something. Who was that? You said that. Okay. So recycled aggregates, the main difference is going to be their properties, right? So your empirical method most likely is not developed based on that. That is the reason you need to study it, right? So that's new construction materials. You are going to do mixed design differences. You are using now you are using a lot of reclaimed asphalt pavement. I think Dr. Sahu said that India has a 2070 target of net zero or something. Is that correct? Yeah. So now you're talking about a lot of recycled materials, lot of contents, lot of warm mix, lot of cold mix, lot of CIR, FDR. I heard a lot of people say that. So the point is your empirical methods are not designed based on that. That's the reason you're going to do that. Mechanistic design, on the other hand, is all the way on the mechanics side. Okay, but is it achievable? We got into the discussion, but I got distracted. I went into transfer functions. Let's go back to this question. Why is 100% mechanics not achievable? Great point. One, soil is not homogeneous. I like that. Keep going. It's not necessarily visual, right? I know what you're saying, but think about an ideal world. When you know exactly how the material behaves, you should be able to predict its cracking. You should be, right? So why can we not do it 100% mechanistic? Soil is not homogeneous is a good answer. Next. That's good, yes. But give me an example. I mean, yes, that's the whole story. Yes. Okay. So you are saying your analysis approaches are assuming certain boundary conditions or something we don't expect, right? Correct. That's number two. What else? There's a lot more. You can keep going. Whose fault is that? Whose fault is that? That's not an excuse, right? I mean, then we need to be better at mathematics then, right, or physics. Okay. So now he's talking about climatic effects. Okay. So, but let's think about this. Climatic effects, if we have really good thermodynamics models and climate models, shouldn't that be taken care of? If that's the reason, right? I am talking about, let's just say we get all the physicists in the best in the world together in a room saying that solve this damn problem, right? Why can't they still do it, is the question. Okay, so practicality meaning you are saying that an engineer may not be able to solve that and stuff. I mean, apply that all the time. Is that what you're saying?
The suggested solution may not be applicable as engineer's point of view.
Yeah, that's what. So okay, so that, but again, that's a valid point. It may not be practical. I am saying it is not impossible. It's not possible. I'm saying so. There is a difference between practical and possible, right? I am saying it's not even possible to do this mechanistic. Practicality, I totally agree with you, but I don't think that answers my possibility question. How many of you have seen a road being constructed? You have, okay? Can you guarantee that the soil the compactor is working the exact same way at every position? Is the being exactly the same and stuff like that? Can you guarantee that the mix that you tested in your IIT Bhubaneswar lab is the exact same that's being put in the road and stuff? Do you know? So those of you who have worked on mixed designs, asphalt mixed designs and stuff, there is something called, the target mix design, and there is something called the job mix formula. I don't know what the term is used in India, unfortunately, but the actual formula that actually goes in the plant is actually different from what you are constructing. So you build all your models for something, the road is constructed with completely different material, right? That's the reason it's not possible. You don't have the answer, right? You are trying to do a 3-point or a 4-point bending test, saying this many kilonewtons acting at 50 hertz, blah 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 and stuff. Now you are having an entire traffic spectra in the road, right? Traffic spectra is completely different, right? So we have so many unknowns that it's not possible for us to do that. That is the reason mechanistic design is not possible, right? We just don't have all the inputs. Those of you who have done Ashto Road 1993 or something, you know there is a reliability factor in there, right? Right? You know why the reliability came into picture? The reliability actually came into picture by saying that they targeted some kind of a testing in the lab and under controlled conditions and stuff, and they actually went and measured those conditions in the field, and the difference between those two is actually the reliability, the S naught square that you see and stuff like that, right? So mechanistic is just is a white elephant. It doesn't exist. Okay, the best we can do is ME, right? We have to go as far as we can with our mathematics, and then we use, and then magic happens, and then cracking, right? That's basically what it is. So if you go into MEPDG or pavement mechanistic empirical design, there is something called global calibration, there is something called local calibration. That's where this is. Why are all these states suffering to do this? Is because not everybody has been able to do successful local calibration. Okay? Okay, how many of you know anything at all? I mean, okay, I think that's a bad question. How many of you have some exposure to asphalt mix design? Some. Okay. That's not a big enough number for me to do. So let me just do this. Mix design approach keeps changing with time. Okay, there's something called volumetric mix design, which was called the super pave and stuff like that, which is VMA, VFA, blah blah blah, all of that stuff. Now there is something called balanced mix design or performance based mix design or something like that. I'm not going to go into all the details because not everybody is asphalt person here, but the point is you are changing your material input significantly as well, right? Let's just say I am a state DOT and I invested several $1 million today and over the next 5 years to establish my local calibration factors, and I'm like, bam, I got it. Next day my materials engineer says, hey, I'm going to adopt balanced mix design, I'm moving away from super pave. What does that do to my local calibration? It all goes down the drain and stuff, right? It's very difficult. It's not that easy to do this, right? So that is the reason. It's not that, you know, scientists are dumb or people have not paid enough attention. It is just that it's a moving target. It's a very moving target. That's the reason. Typical pavement structures, again, most of you will know this. We are going to focus on base, sub-base, compacted or natural subgrade, and embankment, natural soil and stuff like that, right? Everything below the surface layers and stuff. Or starting from the surface layers, you know, if you're talking about unsurfaced roads or gravel roads or something like that, right? So just a typical thing. Stress distribution. Okay, I think everybody should know this. There's a very little thing. This is for the new master students and new PhD students who are getting ready for their qualifier exam. Do you guys have a qualifier here or something? Is that a research proposal or is it like a knowledge test and stuff? Knowledge test. Okay, good. So that's what I was talking about. So if you're getting ready for that, people actually start saying things like, and this is something I see all the time, I hope a lot of you realize, people say that as we go down in the layer, the force decreases. Is that a correct statement? Stress decreases. Force does not decrease. If force decreases, then the thing will be flying out, right? Force equilibrium has to hold, right? So don't let Newton turn in his grave or something, you know. Be careful about statements like that. So there is stress distribution changes, force distribution does not change, right? Similarly, things like, you know, we will get to this on day 3 and stuff. People say things like, I have a very high resilient modulus, or I have a very high modulus thing. So this is a very strong layer, right? No, it's not. It may be a stiff layer, right? Strong represents strength. Modulus has nothing to do with strength, right? So pay attention to mechanics, pay attention to physics, right? Modulus is a slope of the stress and strain curve. Strength is the maximum stress value that the material can take. Do not make them the same. So a gravel layer, yes, it may be stronger because you just got lucky that the shear strength is also higher. But don't say that a higher modulus means that it is stronger. Say higher modulus means it's stiffer, right? But then there is a difference between what is stiffness versus what is strength. Sorry, what is stiffness versus what is modulus. Let's read that right now. Actually, this is a good time. What is stiffness? Resistance to deformation. Right answer. Give me the mathematics. And you don't say. You finished your PhD. Others. K is equal to F over delta, or delta. Yeah, K is equal to F over delta, right? Or F is equal to Ku, which is the fundamental of what? Spring and the entire finite element method. Those of you who have studied it, right? Stiffness matrix is basically what it is, right? What is modulus? Oh, wait, no. What is the unit of stiffness then? What's your name next to Chanchal? What's your name? Raki. Raki, what's the unit of stiffness? F over delta. What's the unit? Meter. Newton per meter. Good. Now let's talk about modulus. What is modulus? Stress over strain. Young's modulus, basically modulus, stress over strain. What is the unit of stress? Pascal is Newton per meter square. And what is the unit of strain? Unitless. So what is the unit of modulus? Newton per meter square. And what is the unit of stiffness? Are they the same? No. Case closed, right? Stiffness is not equal to modulus. The problem with us pavement engineers is we always try to talk about them as the same language. You need to remember this. You know why you need to remember this? Because we actually encountered this in Tanmoy's research. He was trying to design some springs for his mold to support and stuff, and he had a stiffness. And I said to model it in Abacus, which is a finite element based software, where the layer is assigned a modulus. You can't equate them directly, right? That's going to be useful because we are going to look into all of that. When you do a design of a pavement, flexible pavement, modulus is a very important component. It's called elastic modulus. We'll get into resilient modulus. Rigid pavements, again, here researchers, what is the unit? What is the equivalent input? Not modulus, something else. What is it? It's not resilient modulus. Modulus of subgrade reaction. Do you remember what that is? Do you remember the unit of that? Meter per meter cube. Now we are throwing another meter in there, right? We must be something seriously wrong with us, right? So you have to understand in your subgrade evaluation what you are studying and where values are coming from, and then you are going to be able to compare things and stuff. right? So we'll take a look at that. So surface loading, you know, in the pavement, as you go down, the material quality decreases, right? Lowest material at the top and the highest material at the lowest material at the bottom, highest material at the top, because that's where the highest stresses are, not highest loads are. 90% of master students or initial PhD students will say the loads are greater at the top. The answer is no, loads are same everywhere, otherwise your system is going to be fly, right? So very strong, durable, impermeable, manufactured, expensive. Strong, free draining, manufactured, less expensive. Okay, there was in transportation geotechniques or in general geotechnical engineering, if somebody tells you what is your biggest enemy, right? Water, right? So there was a very famous scientist called Sedergreen. He wrote a lot of books on drainage and stuff like that. His famous saying is that a pavement engineer needs to worry about only one thing: water, water, and water. Right? So drainage, free draining. Let's talk about railroads. Some people actually asked some questions about railroads and stuff in their homework 0 and stuff like that. You know what a ballast layer is? The rock layer. That's called ballast. Right? Do you know what is the primary function of a ballast layer? Drainage. It's not load transformation. It is, I mean, it does transfer load, but the primary requirement for selection of a material is drainage. Because if water doesn't drain, what happens? Swelling is very soil dependent. It may not swell. Maybe, yeah, in black soils, yes, I would agree. What happens? When water cannot drain, what happens under loading? Pore water pressure develops. Higher the pore water pressure, what happens? Lower the effective stress. And what governs your shear strength? Effective stress. So what happens? Your shear strength collapses. Right? So water is very important. We need to be careful about that. Then comes the question again in day 3. These are all open-ended. I mean, this today is all about introduction anyway. The point is, we're going to talk about this, is when you do a resilient modulus testing on an aggregate layer, should you be worried about a drained condition or an undrained condition? Why? Right answer, but why? It should not accumulate water. Base layers are designed to drain water, right? So it's a drain test and stuff. Well, I should not say drain test, because drain test means it's a very long. It's actually an undrained test because you don't worry about the thing. We'll worry about that later. Subgrade. Always, I prefer this. Again, your courses may be different. I always prefer to divide subgrade into 2 parts. One is called the natural, that I don't touch, and one is called the prepared subgrade or compacted subgrade. Because when you are building a road or something, you're only compacting about 2 feet, 24 inches maximum, maybe 36 inches, not more than that. Below that, the world still exists, the earth still exists, right? So always divide that into 2 parts. Why worry about subsurface layers? Nearly all the measures of pavement performance are based upon observations at the surface of the pavement, right? We are riding on the roadway, we are seeing the effect on the roadway, which is rutting, which is cracking, which is ride quality, right? But if you go back to the Ashow road test, the percent of total surface rutting, if they divided it, they said asphalt layer was 32%, granular base was 18%, sub base was 39%, subgrade was 11%. So 1139 is 50 plus 18 is 68%. 68% of the rutting was actually coming from the subsurface layers. That's why transportation geotechnics is important. Now I will tell you one thing, it is possible to kind of mask over this problem sometimes by building a very thick concrete slab or doing a really big, cement stabilization of a base or something and then build an asphalt. It's possible to sometimes overcome this. But then the problem is, are you doing your job as the engineer to do the most economical, sustainable, resource efficient design? The answer is no, right? So that's the reason you need to look into that. Okay, geotechnical influences on flexible pavement distresses. Let's take a look at this. So fatigue cracking, also known as alligator cracking, right? Because the cracks look like alligator skins, stuff, right? Insufficient base stiffness or strength, yes. Insufficient subgrade stiffness or strength, yes. Moisture drainage problems, yes. Freeze thaw conditions, yes. Swelling does not do fatigue because fatigue is a repeated application, right? Swelling probably happens once. Swelling can do shoving, swelling can do other things, but not really bumps and stuff, but not that. Contamination, erosion, no. Spatial variability, not really. Rutting, again, weak layers, moisture damage, freeze thaw. Okay, by the way, how many types of rutting are you familiar with? 2 types. What are they called? Say it again? Yeah, I mean, yes. So it's called primary rutting and secondary rutting, right? Primary rutting is what happens inside your asphalt layer. Secondary rutting is actually it's going underneath. Primary rutting means your mix designer did not do a good job, or your asphalt compactor did not do a good job and stuff. Secondary rutting is you're going deeper, right? So that's what we are going to worry about primarily, right? Corrugations, again, because thin layers and stuff that can actually sometimes make lead to these undulations and stuff. Bumps, freeze thaw, swelling, spatial variability, depressions, potholes, roughness, all of that and stuff like that. So all the aspects that you see are going to be because of, I mean, all the distresses you notice somehow can be affected by geotechnical layers and stuff like that. So you just have to be careful when constructing, because if you have a problematic, infected wound or something, no matter how many band-aids you put over it, it's not going to be fixed. You need to cure it, right? So there is no other cure. Rigid pavements, okay, fatigue, punch outs, which is seen on continuously reinforced concrete pavements. Pumping is a big erosion issue. Faulting, which is the elevation difference between the slabs and stuff. Roughness and whatnot, all of that. So if you see here, even in the rigid pavement, moisture and erosion are basically the two that have all excess. If you go into the subgrade strength, see how it doesn't have all excess? That's because several of rigid pavement distresses you can get by with weak subgrade. It's because the slab carries most of the load, right? It's not as demanding on the subsurface layers and stuff like that. This is on rehabilitated pavements, AC over PCC, mostly reflection cracking and roughness and stuff like that. So this is just some information. Some terms that you should be familiar with. Okay, optimum moisture content, maximum dry density. You know that, right? Everybody knows that. Triaxial testing. Okay, let's talk again. This is just laying the foundation for the future stuff, right? So you have learned about when you talk about triaxial testing, you draw more circles, right? So if you want to draw more circles, you have, who remembers what's the x-axis? Stress. Principal stress. Normal stress. What's the y-axis? Tau, right? and then you do this, and Rakhi just said this is sigma 3, sigma 1, sigma 3 prime, sigma 1 prime, like other case and stuff like that. That's what you just said, right? So these are called principal stresses, right? What's the definition of a principal stress? On what? On a principal plane. So what is the principal stress? The principal stress is the normal stress acting on the plane on which shear is 0. Why can we plot a cylindrical triaxial data using more circles? The loads that you are applying on a cylindrical triaxial test, right? So this, you call this what? Sigma 3, you call this sigma 1 and stuff like that. We'll get into all of that details and stuff, right? Why? Why do we write sigma 3 and sigma 1? Why do we by default say that these are principal stresses? Have you thought about it? You know sigma 3, right? Confining pressure. Why is the confining pressure not just a normal stress? Why is it principal stress? Normal stress is perpendicular to the surface, right? There is no shear on that plane. So in a cylindrical triaxial testing setup that you are applying, you are not applying any shear on those planes. And what law is that? What are you using for confining the devices you have here? Is it air or is it water or is it oil? What do you have? Water, some water, mostly water, probably air or something. What law was it? That Pascal's law, that any point the stresses are normal in all directions. That is the reason the stresses are normal here. That is the reason there is no shear stress. That is the reason you can plot it using more circles, right? Because that by default becomes the principal stresses, right? And because you are doing cylindrical sample, your intermediate and minor principal stresses basically become the 1. 2 doesn't exist. It's the same as sigma 3, right? So that's what you're talking about. Okay, shear strength, we already talked a little bit about this, right? It's the maximum stress that the material can undertake, right? So then you'll go into these things called more Coulomb envelopes. We'll get into all of that. You'll draw this and you're like, okay, there is no point that's above this and stuff like that and whatnot and whatnot. So we can talk about that, those things, right? Then modulus versus stiffness, we went a little bit that. I don't think in this class, in this course, I'm going to go into PG grading of asphalt much, but that's the performance grade, which is a way of defining asphalt like quality and stuff. And then pavement distresses, you know this, you know this. So because we are going into mechanistic, empirical, and discussing all of that, what are the primary responses that we care about? What are the responses, the critical pavement response parameters? Do you remember those? Horizontal, tensile, what did you say? Strain. Okay, so epsilon T, where? Bottom of the asphalt layer. Okay, good. So we have this. Let's just do this. We have a HMA. We're doing a base. We're doing a subgrade. So you're saying this. Then vertical strain. Okay. Where? Right here. Subgrade. Okay. Sure. What else? What else? Tensile stress and strain where? Top of the subgrade. Good point actually. Can subgrade take tensile tension? Can it be? What is the base nature? Base is a unbound layer. Can an unbound layer take tension? Yes, yes, for sure. But that's actually a very good point she just raised. How many of you have run a what's it called? It's called IIT Pave here, right? IIT is IIT Pave finite element or layered elastic? Layered elastic. So have you run IIT Pave? I can guarantee that if you run it, you will see tensile strain in the base layer. That is a manifestation of layered elastic analysis theory. That is the reason when we go into IIT Pave and stuff like that, the finite element, we will go and we will say that the moment it goes into tension, cut it, redistribute, because tension is not possible. I am glad you brought that point, because yes, theory gives you that, practical is not possible, right? So we have to know the difference between the two, right? So okay, by the way, this is correct, epsilon v, okay, but there is actually some modern, not modern anymore, there has been research that actually shows that compared to epsilon v, it is actually sigma v on top of the subgrade that is more important than epsilon v, the stress, because there is something called subgrade stress ratio. We will go into that tomorrow. How does the stress compare to strength? QU, unconfined compressive strength, you know that, right? So where are you with respect to that? How does that ratio affect your behavior? We'll get to that tomorrow during subgrade evaluation and stuff like that. So SSR is a very important concept, okay? So these are the critical pavement response parameters that you should be interested in. So anytime you have to build a, you're analyzing a pavement or something, you're going to pick these, and then what? These are used to predict. What are these, by the way? Response or performance? Response. So what are they used to predict? Performance. That's where the transfer function comes into picture, right? So you're going to pick these, and then we are going to predict how this is going to lead to alligator cracking or fatigue cracking, subgrade rutting. That is actually another one that gets measured here, is actually the deflection at the surface, delta at the surface, right? Because we are getting into all this discussion, let me ask you another question here. What kind of a phenomenon is rutting? Vertical deformation, that's correct. Elastic or plastic? Plastic? Yes. What kind of analysis is any layered elastic analysis, like IIT Pave, Ken layer, all of that? So we are doing an elastic analysis to predict plastic deformation, right? As long as we know our limitations, right? We are doing an elastic analysis and predicting plastic deformations. Just know that. I am not saying that. Why? Because doing plastic modeling is extremely difficult. It is prohibitively difficult. That's where the practicality issue comes into picture and stuff. We are not going to be able to do that. But we need to remember there are differences. We need to worry about those things. Can we relate the response and performance in FEM modeling? Again, it is all dependent on how good of a hand material. If you are saying, can I use FEM to predict crack propagation? Yes, you can do that. You can do that. But again, what is FEM? It's a continuum model, right? The moment there is a proper cap, proper crack, continuum falls apart, right? That's where you have to go into discrete models and stuff. That's very different, right? Which is called discrete element and stuff like that. Okay, I posted this for you all yesterday. You should have downloaded this already. Please keep this in your archives. It's it's a very good read. You'll enjoy this. Okay. I think you know this. Several types of flexible pavement. This is just background stuff. I don't think we need to go over this anymore. Conventional, deep strength, full depth. Okay, how many of you have heard of the term called perpetual pavement? What is a perpetual pavement? That's it? Now you're throwing complicated stuff at me. Okay, perpetual pavement is, it's perpetual. It's like Pitama Bhishma, it doesn't die, right? It can go into what is known as the Sarasarja or something, it will not die, right? How does a pavement die? Fatigue cracking, rutting, right? Fatigue cracking, yeah, there is something called top down fatigue as well, but mostly traditional physics says it is bottom up. So now you have a good enough layer that is bottom, it's rich at the bottom, so the strains are, even if it's big strain, because it's rich, the modulus is low, it doesn't crack anymore. And the rutting is, you have a rut resistant layer. So all you need to do is a perpetual pavement is just do some milling and stuff, just some surface maintenance and stuff, it will stay, right? So the point is, in a perpetual pavement you never ever get to the subgrade layer or the base layer, because that beats the purpose and stuff. So there you have to have a proper design before you start building. A lot of times you do a line stabilization of the subgrade, which you do like a full depth asphalt and stuff like that. This is just, again, background information for you all to keep on top of things. Rigid pavements, JPCP, jointed plain concrete pavement, reinforced concrete pavement, CRCP, PCP and stuff like that. Again, as I said, rigid, it's a little bit forgiving, more forgiving for your mistakes on the underlying layer stuff. Erosion is a big issue, pumping is a big issue, strength you can get by. Unevenness is a big issue. If you have really varying properties, that causes a lot of problems. And then curling and stuff becomes big. It's composite pavements, major material types. Again, this is just background information for you to keep. I hope everybody is kind of familiar with the basic definitions of soils and stuff, the classification, how it works and stuff. What does plasticity mean? What is high plastic versus low plastic and stuff like that. That's something we're going to use. Soil classification, density, water content, stiffness or strength, resilient modulus, modulus of subgrade reaction, thermohydraulic properties, drainage coefficient, permeability, coefficient of thermal expansion, performance related properties, which is repeated load, permanent deformation characteristics and stuff like that. What are special challenges? You have expansive soils. That's India, a lot about it already, right? Frost susceptible soils, materials, right? Freeze conditions. What is the primary requirement for freeze thaw to happen? Say again? Water, one. Water, okay, let's just call it water. Second, low temperature, otherwise it's not going to freeze, right? Third, water, crack leads to water, yes. Third, say again? Air voids, how? It is lower than what? Are you talking about the asphalt layer? I don't understand how it is. Oh, no, no, no. Oh, so you're talking about the ability to capture freeze thaw stresses. That's a different thing. I'm talking when will freezing happen. Yes, you are right. If there is air voids, there is a cushioning effect, the shock absorber basically, like you can absorb some shock. You're right. But I'm not talking about that. I'm talking when is frost a problem? Frost heave is a problem. Water, low temperature, and the other is the layer should have enough permeability for water to be moving through it and have that kind of a problem, right? You know the interesting problem, the freeze thaw and frost susceptibility and all of that is not as big of a problem on clays. It's actually a bigger problem on silts. You know why? Because clay has such low permeability that water actually does not even move far enough for you to have that problem. Silt has just the right combination, little bit higher permeability that water can move and it is still frost susceptible and stuff like that, right? So frost susceptibility matters. I mean, I don't think frost is a problem in Odisha, right? We barely get below, what, 15 degrees Celsius or something maybe, right? Karst topography, pumping soils, highly fluctuating groundwater conditions, like these are all things that are going to affect your soils and stuff. Already said that. Collapsible soils, again, metastable structures, large volume decrease when saturated and stuff. So this is all problems. This is actually an interesting plot from actually from AASHTO 1993 analysis. This is subgrade CBR, required base thickness. Okay, so AASHTO 1993. If you don't remember that, maybe you should go and review. You put a subgrade stiffness and you basically calculate the structural number required to protect the subgrade, right? We're talking about philosophy here, right? The entire philosophy there, folks, was what? Protect the weakest layer. That is AASHTO 1993. You just protect the weakest layer. There was no focus on what happens within the asphalt layer, what happens within, like any cracking happens in there or something. There is no such thing. It is basically protect the weakest layer, right? So subgrade CBR, as the subgrade CBR increases, your required base thickness decreases significantly, right? But this is base percentage of overall structural capacity. So when the subgrade CBR is very high, your base does not have to take a lot of structural capacity. Your subgrade is also contributing, right? Like when you have that sibling who doesn't make a single penny, you have to make most of the money to support the house, right? That's basically what it is, right? When both are supporting equally, not the entire load is not on one person. Base CBR required AC thickness. Remember, see, as the base CBR increases, AC thickness goes down significantly, and also the contribution from the base layer actually goes. And the base overall structural capacity can go up to 50%, folks, for a pavement, right? So up to 50% of the structural capacity comes from the base layer itself, right? That's why I said in flexible pavements, substructures play a much bigger role than rigid pavements and stuff like that. Drainage, right? Huge issue. That's why you go into, like, there are big fields. There is fields on, how do you construct edge drains? What are the wicking geotextile applications and stuff that will actually remove water and stuff? Because there is a lot of this actually is this is by McAdams. See, the roads can never be rendered thus perfectly secure until the following principles be fully understood, admitted, and acted upon, namely that it is the native soil which really supports the weight of traffic, that while it is preserved in a dry state, it will carry any weight without sinking, and does not in fact carry the blah blah blah, and that thickness of a road should only be regulated by the quantity of material necessary to form such impervious covering, and never by any reference to its own power of carrying the weight. That was the underlying philosophy. Actually in India the word macadam is still used, right? I think it's WBM, WMM and stuff like that, you still use that, right? That's the engineer, right? That's the UK engineer, macadam. He actually developed all of these things, right? The erroneous option so long acted upon and so tenaciously that placing a large quantity of stone under the roads, a remedy will be found for sinking into wet clay or other soils. In other words, that a road may be made sufficiently strong artificially to carry heavy carriages, though the subsoil be in a wet state, and by such means to avoid the inconvenience of natural soil receiving, has produced most of the defects in the roads of Great Britain. Essentially, if you think you can put enough band-aids to cure an infection, you're going to die. That's basically what it is saying, right? You have to fix the underlying problem. Macadam, 1820s, we're in 2024. 204 years, we still haven't solved the dam problem, right? That's the thing. Sources of water, seepage from high ground, vapor movements, capillary action, rising water table, these are all things that you will have to be careful about as engineers. How do we control, reduce moisture, prevent moisture, use material design features that are sensitive, insensitive, and quickly remove moisture that enters the pavement system. So all of these things are again part of transportation geotechniques, right? You have to design drainage, you have to worry about freeze thaw, you have to worry about frost heaves and stuff like that when there is things. Structural failure, functional failure, again just introduction for today so that we can get into all the details tomorrow and onwards, so that we don't have to cover anything. Significant load related versus environment related, right? Environment related is something we really have to worry about too, because it does affect, right? Asphalt, you'll just have thermal cracking. If you don't do anything, low load, still have thermal cracking or block cracking and stuff. Failure can be functional failure or structural failure. This is something we already discussed today. In functional, people always worry about ride quality and cracking and rotting, all of that. We do not have good enough models to talk about surface friction. Surface friction is another very, very important component of functional. We assume that it's going to be taken care of by our materials. We're going to have good enough aggregates that are polish resistant, that are going to provide the friction and stuff. That's why you do the friction testing and all of that stuff, right? But that's another very, very big functional thing. Present serviceability index stuff, just performance curves. Don't think we're going to use that much in this class. I'm sure you have seen this. With time, there is some form of drop, and this is where maintenance comes into picture. Like at what point you do the maintenance so that you optimize the schedule rather than spending a lot of money. I think this is the last slide on this block, but the whole idea here is I stand by what I said. If you are doing an empirical design or empirical method and you are still within this circle, you are still okay. The problem happens when you do these. You have no idea how the material or how the system is going to behave as the load increases, as the number of freeze thaw cycles increases, as the number of rainy days increases, as time increases, just oxidation of the layers happens and stuff like that. You don't know any of that. That's when the problem is. Extrapolation. How many of you have taken a linear regression class in your life? Some kind of statistics class, right? I'm sure your linear regression professor also told you that regression, do not just blindly extrapolate. Extrapolation is danger. Regression works in the area that you're talking about, in the domain that your data was developed for. That's basically what this is. Last thing for this block, railroad track, right? I told you this. Close your eyes and imagine this did not exist. This was just an asphalt layer or something. underneath that it's the same thing. There's no difference. Same concepts apply, same layered elastic theory, same properties, same subgrade evaluation, same shakedown, all of that happens. There are some challenges, there are some other things. One of the biggest challenges is railroad ballast is very, very open graded, and open graded materials are extremely difficult to work with. If you want an example, you know, marbles that kids play with, marbles, if you put it in a mold, Proctor mold, and do a hammer on this side, the material will just raise here. You bump it here, it just raise here. That's what railroad ballast is. It doesn't compact. So you have to vibrate it to the optimum configuration and stuff like that. That's the primary. Otherwise, pretty straightforward stuff. There is a phenomenon called ballast fouling. Okay, it's called ballast fouling. F-O-U-L-I-N-G. Fouling. It basically means it getting dirty. Okay, and ballast fouling can happen because of many reasons. The ballast itself can break down because it's a very open graded material, right? It can break down, voids will be filled, or subgrade may pump, or you're transporting coal and coal may spill. All of that can lead to ballast fouling. Okay, ballast fouling is a very bad phenomenon. Okay, but one thing you really need to understand is, if you have a fouled ballast in the middle of a desert, right, it's dry, the shear strength of that ballast, or sometimes the modulus, may actually be better than an open graded ballast, because now the fines are stabilizing the matrix a little bit, and the system is actually more like a well graded system than an open graded system. The problem happens when it rains, hence water is another thing. When it rains, there is a lot of lubrication happens at the ballast, and then the thing starts falling apart. And also, if it rains and if it is fouled, then water cannot escape. If water cannot escape, under dynamic loading there is excess pore water pressure. With excess pore water pressure, you have reduced effective stress. All of that happens, right? So that's basically what this is. Okay, so that was this block. I think, again, reminder, those of you who haven't sent this, please send it in today. Before tomorrow, I want these things. We're going to break at 1, right? Yeah, I think I'll take a 5-minute break. And then we can probably go a little bit more and then break for lunch or something. So that's, yeah, let's take a 10 minutes break, folks, and then I need to drink some water. And then we'll finish the last thing. We don't have very long, maybe 20 more minutes, and then we'll break for lunch. Okay? All right, thanks. ओहो मु तो किछि करनी माने करिवे ना ओह माय गॉड Okay, let's get started. I don't think we'll go more than 15 more minutes, 15-20 more minutes, and that will be, and then we'll break for lunch and then tutorial. So we covered good ground today. Here is what you're going to have for tomorrow. This is a paper I'm going to send most likely during lunch. It's only a 5-page paper, very short paper. Please read this before coming tomorrow. It's by one of my former professors. This is a very old paper, sometime in the mid-90s and stuff like that, but it's a very, very relevant paper about what is the overview, what should we watch out for, what is mechanistic empirical, and what's the framework and stuff like that. And this is written for a pavement design point of view. The same thing holds for railroads. It's exactly the same, right? What needs to be watched out for and what needs to be done. We have had a lot of discussions. So I'm going to do this Menti for you guys right now. So pull up your phones. Give me a few. This is a word-based question. So give me a few disadvantages of empirical pavement design approaches. It's typing based, so just type it up. Complicated to understand. Based on past experience, doesn't consider actual pavement responses. Okay. Projection directly for other conditions. Okay. Oh, one was hidden over there. Hold on, I need to change something here. Change my Menti slide. Keep going. It's not going to affect your thing. Oh. This is the problem. I can't even find my there. There. Swap displays. No. Escape. Design, show QR code, boom, there. Okay. Cannot be generalized for different traffic, climate, or material conditions, implemented for specific area or material specific, too much mathematics. Actually, it's not, because we're talking about empirical. So it's mostly based on performance curves and stuff like that, so trends. So that is actually not correct. Might not be valid for all places, wide range of traffic. Where are the others? How do I see all the others? Is it scroll? I'm relatively new to this Menti thing, so I'm trying to figure out myself. That's over there. I don't know why it is doing this. Oh, okay, it's a big scroll. Okay, let me do this. I'm going to connect this. And we're going to drag this over there, and then we can scroll this right now. Okay, valid only for limited geographic and environmental conditions, limited applicability flexibility based on experiments, so not completely realistic for future conditions. Doing all sorts of same empirical design would not work for different locations. Region where past data is not available, limited applicability, does not consider climatic variabilities. This I don't know. I mean, if you have data across other climate stuff, probably valid, right? So you may be able to handle some of them. Again, this is just an discussion, folks. Based on experiment, not completely realistic, does not for future conditions. Okay, yes, does not cover large field. Change in traffic pattern, limited geographical, yes, based on past experience, blah blah blah, may be applicable. Incurable, we're not considering. Okay, I think most of you got the gist of it. I think except for that mathematics thing, which I don't necessarily agree, I think all of that is probably correct. So I think I'm going to try to summarize this and send it to you all. That way you have it, what the entire class thought. So yeah, it's just a refresher of things. The question is it all bad? It's actually based on actual data, which is a good thing, right? It can be reasonable if used in the data range, and sometimes it's faster to rely on experience than to investigate the cause and stuff, right? So what I'm trying to say is, yes, I mean, from a pavement design perspective, we all agree. I mean, there is no, I'm not saying empirical ways, but what I'm trying to say is, give this deeper thought when talking about empirical as well. Sometimes in some scenarios it may be good. Let's just think about a special case. Let's just say that the state of Odisha comes across a very special recycled aggregate, a waste aggregate that can be used here. It's not commonplace in the rest of India, rest of world or something like that. They don't have to worry about developing general performance equations for it and stuff like that. They would just test it here, develop some kind of a performance curve, and then just use it in the. It's perfectly fine, right? There's nothing wrong with it. You just have to give that a little consideration. But yes, we all agree on that. Mechanistic solutions to all problems, is that correct? You know, Bhubaneswar started this, the single layer point load application and stuff. Then Burmeister went into this and said it's going to be multi-layered and stuff. He started with 2-layer, then he later wrote a 3-layer, and then he that was extended to n layers. There is differences in the friction between the layers and stuff like that. In India, there has been a lot of very high work that has been done by in this field. I mean, who was Animesh Das's advisor? Dr. Reddy? Pandey, B.B. Pandey, right? Yeah, so he did a lot of work. Animesh Das, Dr. Animesh Das from IIT Kanpur, his work is a lot on this. His book actually goes into a lot of this theory and stuff like that. I actually use his book quite a bit. So in India, there has been a lot of work as well. But it is all, again, layered elastic analysis and stuff. And then Westergaard on the concrete side, slab on grade and curling theories and stuff like that. The concept of dense liquid foundation and stuff. I don't know, some of you know this or not. Winkler foundation and stuff. Do truly mechanistic design methods exist? Right? So based on that, again, this is another one. Let's try to do this. I am really having trouble with my cursor in this computer. okay, there it is. Hold on for a second, there is something wrong here. Info reload. It's not giving me the option to start it. I need to figure out tomorrow. There it is. Okay, let's go. Oh, I need to again remove that thing. I hope I can figure this out. Let's start from here. We'll go one by one. Based on many assumptions, 100% dependency because there is some human errors. I am hoping you're talking about human errors in construction and stuff like that, not the mathematics necessarily. Replicate in the same conditions, performance can't be determined. See, again, this is not something I necessarily agree with, because if you have really good models, then you may be able to predict from response to performance as well. That mapping may be possible as well. But yes, mostly that's practical. Not homogeneous, quality control, assumptions and too much calculation, doesn't consider variation in climatic condition. See, this actually is not necessarily true, because we in the MEPDG, the pavement mechanistic empirical pavement design guide, there are very good climatic models. There is something called enhanced integrated climatic model that actually takes, rainfall data, solar radiation, and all of that, and tries to model that. So it actually works. Mostly theoretical, we get in mathematics, maybe not be possible in real life. Maybe representative sometimes because the assumptions, yes. Predict the inelastic nonlinear response of material because we assume elastic and this is a very interesting question. This is the current practice, what we talked about, right? Does not mean we cannot do it, right? That it is possible. People have done complex models analysis using plasticity theory and stuff. It is prohibitively expensive computationally. It takes a lot of time, but still can be done. It's not practical, yes, I agree. Possible, yes, possible. Actual field condition, response performance, blah blah blah, reliability issues, maybe how to incorporate reliability, I guess. Yeah, the inhomogeneous and stuff like that might vary in field scenario. Okay, mostly pretty good. So I think we are all on the same page. Couple of more things I want to cover. before we can break for lunch is this is the overall model. This graph is from the paper I will give you during lunch. So you will see this. Inputs, you saw that material, traffic, climate, all of that go into the structural model, which is what your IIT PAVE is, your layered elastic analysis. You can do anything, right? That your finite element model, whatever you do, pavement response, sigma, epsilon, delta. Then you go into transfer functions. That's the most important part. Transfer functions. How do you develop them? What is the relationship? What are the factors? Because if you go into the old asphalt institute method and stuff like that, it's actually, it just says number cycles to equal to a function of tensile strain at the bottom of the asphalt layer. It's a fourth power or something like that. It's that simple. You can still do it if you're doing like a, just a regular rural road design or something, quick design. You can do that, no problem at all. But things are not as isolated, so that is the reason mechanistic empirical pavement design considers many things, and then distress performance, and then design reliability and design iterations. So this is the reason at the very beginning today I said something about we should know the difference between design and analysis and performance prediction. Mechanistic empirical pavement design is analysis and performance prediction, because you are selecting a section. You are not starting from scratch and the system is not saying, okay, use 8 inches of aggregate, use this many inches of asphalt. You are saying, what if I use this asphalt, this much, this much, this much. You test it, it works or does not work. You have some standard service performance standards. It either works, does not work. If it doesn't work, you reiterate, right? So that is the reason I personally, I've seen, I don't remember who I learned this from, but whenever I write, I don't call mechanistic empirical pavement design, I actually call it mechanistic empirical pavement analysis and performance prediction, because that is what it is. You analyze, you predict, and then you reiterate. That's how you optimize the design. Okay, the very last thing, it's actually, this is another way of the same graph, and it talks about pavement smoothness here, and you can set failure criteria and design reliability and here. Okay, the very last thing we need to do is, I haven't talked about the levels of input in mechanistic empirical pavement design. Okay, again, this is going to be a little relevant when we go into other blocks. So there are actually 3 levels. So level 1, 2, and 3 of material inputs. Okay, what are material inputs? Okay, maybe it will take more than 10 minutes. How do you test the construction of a subgrade on a roadway in the field? Who has worked in the field or any internship? How do you test it? Density. Very good answer. You do? Do you do CBR in the field? So don't say research answers. Density is the only one I know of right now. You know. DEC do it like a right? If I ask you to give me an equation relating density, elastic modulus, or shear strength, or anything, can you do that? Is there any physics that links density to modulus or strength? The answer is no. You can do empirical. You can say this is my density, this is my thing, this is what the relationship I have. That's different. It's not physics. There is no physics. There is no mechanistic relationship, right? So in mechanistic empirical pavement design guide for subgrade soils, aggregate bases and stuff, density is not a direct input into your mechanics. What is a direct input is your modulus and your Poisson's ratio. right? Those are the two things. So the level of input in a mechanistic empirical pavement design guide, there is level 1, 2, 3. One is you are in a purely research environment and stuff, where you have tested everything for what you are trying to do. Like, let's just say tomorrow IIT Bhubaneswar is going to construct a pavement test track. So now you are trying to characterize the material to construct it. So you bring the soil, you do all the classifications, you do all the shear strength testing, the resilient modulus testing, all the inputs go directly into your mechanistic analysis procedure. That's called level. Okay. Level 2 is you have some information, but you don't have everything. Let's just say the resilient modulus test device breaks down, you can't run it. But what do? You probably are able to run CBR, you're probably able to run DCP, you're able to do something, right? And then you use what is known as these correlation equations to predict from CBR to resilient modulus, to DCP, to CBR, to resilient modulus, to R value, to resilient modulus, to from density to, I mean, something, you're doing something. That's called level 2. Level 3 is when you don't know anything. Now you're just talking about a soil survey report and say, okay, for the district of Khordha, this is the soil type that is there for this kind of a soil. It's a medium plasticity clay or something, or low plasticity clay. For a CL material, a representative modulus value is 15,000 psi, something like that. That's called level 3, right? So you as a engineer will have to decide for what material, what property, what level you have and stuff like that. The unfortunate part is that in the current version of mechanistic empirical pavement design guide, aggregates and soils level 1 input does not exist, because stress dependency of resilient modulus is actually not directly considered. It is just assuming a constant modulus value. On the other hand, for asphalt and for concrete and stuff, you can actually put level 1 inputs and stuff, right? So the way the system is designed is how much confidence you have in your data, level 1, level 2 and level 3. So just keep that in mind, that what level of information you have, and based on that you can do your design and stuff like, or analysis and stuff like that. And then comes the whole concept of global calibration factors versus local calibration factors. What is global calibration factor? Local. What global calibration factor is, this much horizontal strain, this much vertical stress, this is blah blah blah, that actually leads to this much fatigue cracking on an average when I use the national level data to calibrate and stuff. Whereas now you are in the state of, because I live in the US, in the state of Oklahoma versus you are in the state of Arizona versus you are in the state of Illinois, the soils are different and everything. So now you have to take your own traffic condition, your own soil condition, your own climatic data, and then you are now going to say, and you're going to observe a pavement, saying that this is my pavement that is constructed, I'm going to observe it, I'm going to monitor its performance, and then I'm going to map that, and that is where you're going to do what is known as a shift factor. That shift factor is basically the local calibration. You go from global to local, right? That is how all the equations are developed and stuff. And the problem with local calibration is it is extremely effort intensive, money intensive, and it is extremely strategic. Like, for example, a DOT will have to make a plan and go accordingly and stuff like that. If in the middle the DOT engineer leaves or something like that, then things fall apart and stuff like that, right? So that's basically the framework of mechanistic empirical pavement design. So I think that's pretty much it what I have for you today before the tutorial. For the tutorial, it's going to be, I'll just give you a paper, you're going to read, and you're going to just start building an Excel sheet. It may not happen today, you may have to do it at home or do it another day or something. We'll see how much we can do we'll discuss a little bit about it. But yeah, over the lunch I'm going to send you that paper and maybe another handout, and then yeah, let's break for lunch. We'll reconvene after that for the tutorial. Okay, right. Thanks, folks.